Yeah, thank you very much for the introduction, and thank you very much for coming and for your hospitality and for inviting me. It's a great pleasure to be here. So now I said enough nice things. Let's come to physics. The thing I will present today is we will talk a bit about dynamical horizons and the Hawking effect. So essentially, we will kind of marry GR and quantum field theory or quantum theory, and we'll see how that works out. This is a joint work with Cecilia Giavoni from LMU Munich. And I think we should just see what we will present today. Okay, so that's the plan. First, we'll go to the geometric side and discuss a bit about GR and the topics there and why we need dynamical horizons. What are dynamical horizons? Why the event horizon is not the best notion for some reasons. And I will explain that in detail. And for sure, when you have questions, just ask me, or we can discuss afterwards as well. So then we'll switch on quantum theory and look at the tunneling picture. The tunneling picture is a very specific realization with which we can describe the Hawking effect in a very neat way. And it provides an easy generalization to a lot of horizon types. I'll also show that. And then we go to the Hawking effect and see how the tunneling pictures then describe the Hawking effect in the end. And then we will have a discussion and we'll attack the result and see whether it's consistent or not, and discuss a bit why it is actually a very neat picture. I hope it's a neat picture I will present here, and I hope I can convince you today. Okay, so let's just start with dynamical horizons. Dynamical horizons, as the word says, are dynamical, and they are horizons. So in that sense, they provide a more general description than the event horizon. Why? So when we want to do experiments, local experiments, what would we do in principle? We would go to a black hole and measure, count particles there, because then we can say, okay, that's the Hawking effect. But the problem is when we have an event horizon, this is kind of problematic. So what we want to do is always related to a specific Gedanken experiment. I want to also to say a German word here. And so Gedanken experiment is, what is it? We have a horizon and we have an observer which is located somewhere. So we want to make a realistic experiment. And let's go to the Hawking description. So Hawking's notion has event horizons. But how is an event horizon defined? An event horizon is defined like the following. We have a manifold and we have a trapped region, which is when we have a black hole, the region in the interior of the black hole. But an event horizon essentially incorporates two non-local concepts, which is future and past null infinity. That means at infinite past, we define our initial conditions, we let them evolve, for example, like light rays, and then we look at future infinity, so when all time has passed, what light rays come to that. So therefore, we can have two regions. One region is the causal past of the infinite future. That means all causal trajectories which have reached future infinity. And those who have fallen into the black hole will end in the singularity and will not contribute to that. So therefore, the trapped region is the manifold minus the causal past of the infinite future, and the horizon is the boundary. But as we can see, for this notion, we need to know the whole time evolution. This is non-local and this is non-dynamical, because we don't have any time evolution in this concept. This is an eternal state. It's kind of teleological. And so therefore, we cannot probe it by local experiments. And that's a problem when we want to perform actual experiments. But then Hayward came with a very smart, notion, which is called parent horizons. Parent horizons are defined by local experiments, and we can define or probe or localize them by making measurements with light torches. I will explain that later, because now we will go to this notion in more detail. And this provides then a local and dynamical setup. So that's more general. The static case is, of course, covered in that. But here, we can really say, OK, I'm sitting, I don't know, 10 meters away from a black hole and measure particles. Or measure what comes out, if something comes out. OK. So let's go into the detail. How are those horizons defined? And yeah, first we should go into motivation, which is a black hole. In the black hole, we know how the Hawking effect is described from Hawking's notion. And this has also been done by a lot of other people. For example, Penn, Vanzo, and lots of people. And yeah, that's the picture. And this looks a bit confusing at the moment, but what do we do? How do we define it? We take an area, this is dA1, and we look at the null expansion. That means we can have ingoing and outgoing light rays from that surface S1 here, right? So we can take our light rays into the ingoing and outgoing direction. And now we want to check when we drag these surface here along our light rays. This is now a vector field, but we can do it along the light rays and want to see whether this area expands or shrinks. This is what the expansion parameter tells us. This can be either negative when it shrinks or positive when it expands. So therefore, we can define basically three regions. The normal region, which is the region like, for example, flat spacetime. That means when I have an ingoing light ray, which would go like that, and when we drag the surface, it would shrink. So then we can have outgoing light rays, like that, and this expands. So that's positive then. So along the outgoing, it's positive, and along the ingoing, it's negative. And this would correspond when we do the product, it's negative. Then we can have trapped regions or anti-trapped regions. Trapped regions are if the light cone is so bent that even the outgoing null expansion will shrink. So then we have the ingoing is still fine for the trapped region. This will converge. But the outgoing is also so bent that it will converge too. Therefore, both are negative, and this gives positive product. For the anti-trapped region, it's the opposite. So both things are diverging, also the ingoing direction, and that's then also positive. And then we can have a marginal trapped surface, which is 0, right? And this is important because that will define then the apparent horizon in that sense. This is the boundary where the light cone is such that one null expansion is not affected, and therefore it's 0, right? And this will define as the apparent horizon. And when we stack those apparent horizons in time, so we have a lot of those slides, and we stack them in time, we get the trapping horizon. This is the time evolution of all of all horizons, and therefore it's dynamical. So we stack this then, and we see how the horizon evolves, and we get something like a world tube. Okay.
What's this product for the Minkowski space?
Normal region.
How do you quantify for it? If you want to compare curvatures because the black hole to infinity, so this gets 10 to the plus times 10 to the minus gets some value.
Yeah, it depends how long you drag it, right?
Well, but then when epsilon goes to 0, doesn't this tend to a constant?
But the sign constant to be negative or positive.
Yeah.
Oh, so you only can.
It's only about the sign. Yeah. The epsilon just tells you how long you drag that along the vector fields, right? When we send it to 0, it's kind of a differential thing, and then we can stack those differential horizons. Okay, but it's a good question because I will show now the normal region for that. So here we want to discuss trapping horizons, and here we have the normal region. The normal region this is the ingoing, B, and here's the outgoing. So we start here. Here's outgoing, here's ingoing. Here we have our dA1, and we drag it here, so we see along the outgoing, this is expanding and this is shrinking. So to illustrate this again. And now we can define future horizons. Future horizons are such that, future trapping horizons, I should say, it's trapped in the future. So therefore, when we have time evolution that direction, we see that the outgoing is now turned such that it's becoming ingoing. So both are shrinking compared to a delta A1, right? But we can define two different future horizons. One is the outer horizon. That means, what means outer? That is, for example, black holes. Outer refers to where's the normal region compared to the trapped region. So the horizon is the boundary between normed and trapped region. As we have seen, this is marginally trapped. And here, when the Lie derivative along the ingoing light rays are still fine because they're still ingoing, becomes negative at the horizon. The Lie derivative along the ingoing light rays of the outgoing expansion becomes negative at the horizon. This is outer. So therefore, the horizon has enclosed a trapped region, which is describing, for example, black holes. But I should say, these are examples. Those horizons are more general. And when we have outer, we will have inner, right? So an inner horizon is, for example, realized in a big crunch scenario. That means we have a normal region which is surrounded by a horizon. And then beyond the horizon, an observer would say, okay, effectively, the region beyond the horizon is like a trapped region because everything collapses so fast, and at some point, it's so fast that we cannot escape because the collapse is so strong that the escape velocity would reach speed of light. That's how you can think about that. Okay, when we have future, we have past, right? Past are past trapped horizons, so everything is trapped in the past. When we look at the evolution in the future, we see that it's anti-trapped because everything is kind of pressed outwards. Here we see the outgoing null rays are still outgoing, that's fine, but the ingoing light rays are now so bent that it is outgoing also. And we can define outer, and this, for example, would be Whitehall. Again, outer means where is the normal region compared to the horizon. So we have the anti-trapped region surrounded by the horizon, like a sphere. We will only look at spherical symmetric things because spherically symmetric setups, this makes life a lot easier. And we have inner horizons, which is like a Big Bang scenario, like the Hubble horizon. So everything expands so fast, at some point, it is expelled faster than the speed of light, and we cannot get any signals from those regions. So we cannot see beyond the Hubble sphere. So that would be an past inner trapping horizon. Good. And this covers also static null horizons. When we say, okay, this evolution does not need to be very, very fast. And it can equilibrate such that it reaches a null horizon. I should say those horizons, the dynamical horizons, are space or time-like, but the static horizons become null. So they will equilibrate it to weakly isolated horizons, which then eventually in future infinity, when we wait infinitely long, will asymptotically approach the event horizon. But the event horizon, in that sense, is not a local concept. So these are totally local. I can't say where this is in principle. Okay, good. Okay, let's switch on quantum physics. So we see, we now go into the tunneling picture. Let's go to the naive picture first. So we want to understand what tunnels from where to where. Good. I like the example of black holes. I worked a lot in black holes, and the Hawking effect is also done for black holes, so let's do it there. And the very naive idea is for the Hawking effect. Why is that a very naive idea? The black hole is a vacuum solution of Einstein's equation, so there is no matter. We can say, okay, the matter is located in the interior. So that means we need to get, when we have a radiation, we need to get some energy out of the black hole because it's somewhere in the black hole. I don't want to say singularity or something like that. Let's just say it's somewhere in the black hole after the collapse. So here we have positive energy, which somehow goes out. I should remind you, the dynamical horizon is not null. So it is space or time-like. There is the possibility to go out if you think about, okay, this might be a bit weird because it's null. But no, that's not the case. So here we tunnel out, and it's measured by an observer. Why I say tunneling. This is a classically forbidden path. So classically, we cannot escape from these things. But when we see the horizon as a barrier, we could tunnel through that because we have quantum physics. So in that sense, we need to kind of modify the path here. And the path is modified like such that we can think about the horizon area as inducing a pole. And this pole induces a discontinuity in the wave function. But what does it mean? This means like it acts like a barrier. When we have a potential step, we think about that. And we have a classical particle will just, when I throw a classical particle through this wall, it will just bounce back. But when I have a quantum particle, it has a probability to go through the wall and comes out. And this happens because it develops a complex frequency. I get an imaginary part which gives me a non-zero tunneling probability, non-zero transmission probability. That's the idea what we also use in this picture. But there's a problem. The problem is very conceptually, because when we want to define the propagation from here to here, we have to set the initial conditions in the trapped region. But the trapped region is a highly dynamic region. We don't have a positive and negative frequency decomposition compared to Minkowski space. This is, you can say, okay, this is a technicality or a technical problem, but it is not, because we cannot then really describe that in a, let's say, in a good way. So therefore, we use a different picture, which is the picture of Hawking pairs. The Hawking pair says, okay, it's still the same. The observer measures positive energy. Red is positive energy and blue is negative energy. So this is the same, what we measure, what we count. But now we say in the normal region, we do pair creation, and the negative energy particle tunnels through the horizon. It develops a pole there. We will see that. And the positive energy particle is still measured. So that will be totally the same. It is a different description, but this description is very easy to generalize and very good to calculate in that sense. Okay. Questions so far? Too fast? Too slow? Too technical? Okay, good. If you don't say anything, I assume you're happy. Okay. Okay, how we describe the tunneling. Good. So the Hamilton-Jacobi method of tunneling, that's the formalism we want to use. I want to explain now a bit how to use it. That's not a big deal. So, but Manaban, Vanzo, all those guys have done it. So, yeah, let's just see what it is. What we exploit is the WKB approximation for massive scalar fields. That means we have scalar fields, and essentially we go to a quantum mechanical framework here. This is, okay, this is kind of an assumption, but you can verify that. It has been verified actually because the two-point function, you can relate the two-point function to the tunneling probability, the two-point function of quantum fields, to the tunneling probability, and therefore it justifies this ansatz. But of course, this is disputable. If you're not happy with this, we can discuss that. So this will be the ansatz for the massive scalar field. And what we now do, we go into the semi-classical limit. That means we send h bar to 0. We use h bar as a smallness parameter, and we get the dominating contributions by S0 and S1 and all higher orders, which will then be sub-dominant. And now we will also say, okay, when we send h bar to 0, what really matters is that thing here. Sorry. This we can forget about. So the Hamilton-Jacobi method uses exactly this assumption. And then we can plug this field into the equation of motion, which is the Klein-Gordon equation. And we get the Hamilton-Jacobi equation. So that's how we get that for S0. Okay. But now, okay, we have to solve this equation. But we have to think, what are our assumptions? Our assumptions are the WKB approximation holds. What does it mean? It means that the potential does not vary fast compared to the frequency of the particle. And when we think about that in this framework, this means that when we see the horizon as a barrier, that the horizon does not change too fast. So the horizon is not like oscillating or very fast. It is just slowly evolving. So that means the horizon is almost null. It's almost equilibrated. And the dynamics are not so fast that it's very space-like or very time-like. Therefore, we say the particle trajectory, the most probable particle trajectory which can tunnel out are particles which are almost null, right? So if the horizon is almost null, then null particles can tunnel through it most easy way, and therefore we forget about m square and impose the following ansatz for S0. Okay. So yeah, now we have to, of course, do the tunneling. And when we remember WKB approximation, then we can define a tunneling rate, which is given by the imaginary part of S0. Here we have 1 over h bar. This is still the smallest parameter. Essentially, it is. We can compare those two things. And we see here that we get the imaginary part here is like giving us the probability, non-zero probability of going through the potential wall. And that's what happens here as well. And we need to compare that when we want to do thermodynamics. We need to compare that to thermodynamic quantities. So this is, of course, now a bit tricky in that sense. So we adopt the formulation Hartle and Hawking have done. Hartle and Hawking have done the following. They say, okay, I fix an energy, and I look at the probability of having n particles at the energy, and compared by having n plus 1 particles at the energy. And they found that having n plus 1 particles is exponentially suppressed. So that means to get with the same energy more particles is suppressed by this Boltzmann factor. I set K Boltzmann to 1 here. And that they interpret it as we have the emission through the absorption is exponentially suppressed. That's what in the black hole case happens, right? It's, of course, easy to throw something in the black hole, but it's very hard to get something out. Okay, and here the idea is to compare the imaginary part, so the tunneling rate, through with this thermodynamic quantity. The idea is the particles which have tunneled out, is then separated from the black hole. We just say, okay, this will be measured by an observer, and this is the same here. We have some observer, and they count this Boltzmann spectrum, an emission spectrum. So therefore, the tunneling rate is related to this emission spectrum. That's the Hartle-Hawking proposal. Okay, so let's just go into the Hawking radiation, I would say, and see how we. Is there questions? Are there questions? Yes. Yeah. Here.
So the scenario that you're describing is though you have the particles trapped inside the horizon, then they can tunnel out. Doesn't this interfere with the holographic principle that everything happens on this thin layer on the surface of the black hole?
Yeah, the point is therefore we choose the picture of the Hawking pairs. Because at the Hawking pairs, we do everything in the normal region. We do not think about something is tunneling out. We say, okay, this is kind of like a gravitational Schwinger effect when you know that what it is. It's like the vacuum polarization of the quantum electrodynamic vacuum. When you have a big charge, you can polarize the vacuum and you create particles like positive charged particles. Let's say we have a big positive charge. The positive positrons get expelled and the electrons get then collected. So this is, you can think about that in the same way. We have the gravitational field, and the gravitational field allows to rip those two particles apart. This, I would not say, has, in that sense, anything to do with the holographic principle. Or
you call this gravitational
Schwinger effect, yeah.
So in the Schwinger effect, that's why I think people keep debating whether this WKB is the right picture, because as you make m's small,
yeah,
the barrier gets small, and in the Schwinger effect, at least, if it takes the electron mass to 0, it's unsuppressed.
No, yeah, they know that's true.
What happens so So what if you look at the equation of motion there, as you make m equal to 0, what you're really doing is you've got a classical particle that takes forever to fall in. So the tunneling is, well, how long does it take to get back out again? Well, if it's running backwards, it's infinity. So the tunneling part is as well, if you take quantum mechanics, then it actually happens at a finite rate, right? Because there's actually no barrier. I mean, classically, saying particles coming out is allowed. It's an exact solution. Things go in, things come out, photons go in, photons come out. That's not a problem, to running time backwards. But the time is a problem. It happens at a 0 rate. So quantum mechanics in this case, you're having tunneling from a particle that's on the top of a potential with no barrier coming down. That's what your classical equivalent is of your WKB picture, right? If you look at the fine Wilczek, which is exactly what you are describing down. But then you're saying, well, but WKB is equivalent to writing an instantaneous imaginary time suit where you reverse time through a barrier. But if there is no real barrier, then WKB is never a good approximation.
The point is, it is not a barrier as you think like a wall. That's true. But the point is, where do I need tunneling? I don't need tunneling only if I have a barrier. It's also when I have discontinuity in the wave function. So then I cannot really connect those two wave functions outside and inside. So therefore, I need to do that because this horizon, the horizon, I will show that it will induce a pole in the propagation, and the pole in the propagation, I need to have an how is it called? A complex path in order to go around the pole. Otherwise, everything will blow up.
Maybe take a look at how you do your path, because I think in the standard thing, I always have the feeling that the WKB is not obviously consistent.
The
semi-classical.
It has been shown the WKB rate is the same one. So I can use quasi-free states, and the 2-point functions across the horizon will converge to this thing as well. So we get the same result. So therefore we say, okay, we get the same result for the 2-point function across the horizon, and then we say, okay, but then effectively we can also impose that we have a one-particle interpretation, and then we trace it backwards and say, okay, those two results converge in this when we have quasi-free state, so we have some localization, and in that sense, this is then the same. But I understand what you say. When you say, I just use it as an ansatz, then it might be confusing. That's what you say, right? But of course, we have to do QFT, the full QFT. That's what you wanted to say, right? We need the full QFT picture, then calculate that. But when we say, okay, we find the same thing, we can trace it back and say, okay, we can use that. It is justified, theoretically. But we can discuss it later, if you like. It would be very interesting, actually. Okay, so let's look at the Hawking effect now and see what happens. So let's go to the framework. Now we show how this is done. So we start again with the future outer trapping horizon of a black hole and see whether the tunneling, how the tunneling formalism or the Hamilton-Jacobi formalism gives the same results as the usual Bogoliubov transformation, Bogoliubov coefficient calculation Hawking did. Okay, we choose the Bodine metric here. The Bodine metric is very powerful, and why? I should explain that. We have this thing here, this placeholder xi. This placeholder xi is for outgoing and ingoing. We can plug both in. And I said, okay, we've said that one direction is the good direction, so it's not affected by the trapping. This we'll choose here. So when we have black holes, we'll choose the ingoing direction here. So this will be U, 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 right? And for the past horizons, we'll use the outgoing direction, and this will be for black hole it will be V, and for the past horizon it will be U. Sorry for that. But the other thing is we need to have a coordinate neighborhood which does not have a coordinate singularity. Therefore, this term here is very important because we get a mixed term with R and the light cone coordinate. Because when you think about the Schwarzschild solution is diagonal, and therefore we get a coordinate singularity at the horizon. But when we look at regular coordinate neighborhoods, for example, like Painlevé-Goldstrand, we always have the mixed term. The mixed term, in some sense, regularizes the coordinate singularity at R equals RH. Okay, so this is a spherical symmetric setup. We see this does not depend on the angles, this is the solid angle, and here also not. Okay, so the spherical symmetry has another big advantage. It has a Kodama slicing. Kodama slicing is, we can define a vector in spherical symmetric setups, which is null at the horizon, which is space-like in the trapped region and time-like in the normal region. And in static setups, it coincides with a killing vector field. So therefore, it gives us some notion of energy, and that's what we want to use here. We want to use the Kodama energy. So we have in dynamical setups some notion of energy. This is the Kodama vector field. This is the null normal. Integrate over the volume of the spatial hypersurface. And this is how it looks like for black holes or for future outer trapping horizon. I should not say always black holes because then we are trapped in the examples. And we can define another conserved quantity along this vector field, which is the surface gravity. This is a constant at the horizon. This is the radial derivative of CR, evaluated at R equals HR. HR is the position of the horizon. But this CR here has some properties. This has the properties of the specifics of the system, and it has a pole at the horizon. This is important. The pole at the horizon now will give rise to this tunneling picture, and we will see how this works. Okay, so now let's apply that. The forbidden path classically is that we have seen the negative energy particles tunnels inside. So we will make a measurement in the future. Why do I say that? Because we need to adjust now the path such that we have a Feynman prescription at the level of the equation of motion. So we add the Feynman prescription here, and we solve the equation of motion, get the Hamilton-Jacobi equation with this prescription now. And of course, we send epsilon to 0 in the end. Good. We get the classical action here. This is the Kodama energy plugged in, and we have identified those K here. Those K, when we solve the equation of motion, we get two solutions. So this here, I should say, the real part in the calculation of K corresponds to the imaginary part, corresponds to an imaginary part in S. So here, this just describes the ingoing direction. So this doesn't give us anything special, so we don't get a pole. But here we see K2 has 1 over CR, and CR has a pole. CR is basically proportional to R minus RH. So that's bad. This will blow up. And this we have in the integral. And now we have to look what we will do with the integral. OK, so that's important, yeah. OK, let's look at this thing and see what happens. OK, we have the imaginary part here. So I just drop everything else and just the imaginary part. Let's visualize this thing here. OK, what have we done? We do the particle creation in the normal region. This is the normal region. This is the trapped region. Time goes up. The positive energy particles goes away, escapes. It's measured by an observer. And we have negative particle tunnels inside and gets trapped in the trapped region. OK, so that's what we see here. We have the path from R2 to R1. Negative energy particles, so omega is negative. And here we see the pole, R minus RH. If we don't have the Feynman prescription, this will blow up. This will not converge. And therefore, this modification will regularize the integral now. And we see that this is a non-zero imaginary part. And this will now correspond to tunneling, to non-zero tunneling rate. OK, so yeah, that's the tunneling now. And the tunneling rate is now given by this expression. We have shown that before. And we compare this to the thermodynamical Boltzmann distribution. And we see that we get a temperature which is h bar k kappa h over 2 pi. And this is, if you don't know it, the exactly same result Hawking found in his Bogusław analysis. So we found the same thing with this thing. So it seems to be consistent in that sense. OK, but I said it's easy to generalize. Therefore, we just do that, right? So we can look at cosmology, look at cosmological horizons, and we look at the path in a trapping horizon, which is, for example, Hubble expansion. Yeah. So let's do the same thing. What's the path now? The problem is the classically forbidden path is that something can enter. OK? But we want to stick to our Hawking pairs. So something can enter means we measure particles coming from the horizon. Here's our observer. It measures this positive energy coming through the horizon. And so we say, okay, the negative energy particle has been created here. This is just a picture. And then we tunnel through the horizon to the anti-trapped region. The anti-trapped region will take the particle away. Okay. So here the integration should be from R1 to R2. Kappa is now negative in this setup. For cosmological horizons, kappa is negative. Same. Negative energy, same prescription, same result. And we find, okay, we have used the Feynman prescription as well. And we found the same temperature. So I have good news and bad news for you. Bad news is we have two other horizons, so it might be very boring. But the good news is they are different. And let's look what is different. Are there questions up to now?
Try to use this the equivalent of the de Sitter horizon temperature. With RH, you're thinking of a de Sitter horizon temperature?
This thing?
Yes.
This is just the position of the horizon.
But horizon, you mean like in de Sitter space, there's a horizon. Is that the kind
Yeah.
of horizon you have in mind?
Yeah, something like this. Yeah, something like this, yeah. Okay. Good. Let's go to the generalization, because those results were known. This is nothing new. I just presented you the framework. And let's see how we can generalize that, right? Okay, let's go to past outer trapping horizons, which are white holes. Again, we do the same thing. We identify the classically forbidden path. Okay, I'm not a big fan of white holes, so don't take it seriously that it's white holes, but that's at least the realization I know where those past outer trapping horizons are. They can be they occur also in gravitational collapse and some other setups. So this is general for past outer trapping horizons. Right? So don't take it serious that I'm looking at white holes. Forbidden path is now to enter the white hole, right? So we have problems to enter the white hole because the white hole, in that sense, spills just out. Yeah. So when we think about that, that's a classically forbidden path, and we want to use this notion for the Hawking effect. The Hawking effect is the antagonizing effect due to quantum physics, antagonizing the classical, the general relativistic trajectory. So it's kind of, yeah, as you know, quantum physics always tries to become a bit more messy. So therefore, it kind of reverses the effect, the classically favored path. So we go out, we go in, we can go in. So then the expectation is absorption instead of an emission. So don't take it too serious what I said about that's messy quantum mechanics. Quantum mechanics is nice. And so we have an absorption instead of an emission. But the problem is when we think about some specific setups, let's say we have a white hole which spills out particles. I want to measure now missing particles or an absorption of particles. This is a bit messy experiment, right? So how can we perform that? Because we see a constant, we see flow of particles, and it doesn't need to be constant. And how can we say that's a Hawking effect? That's a Hawking particle, and that's some other particle. So in that sense, yeah, let's clean up our experiment. And the good thing is we do a Gedanken experiment. So we can clean it up very easily in the sense that we think about the following way. So we have an absorption in the future. That means we place our initial conditions. We have 10 particles. We shoot them towards the horizon, and then we get 8 back. So we see that's an absorption. But we can also reverse that and can say that's an emission to the past. So we can say, okay, I start in the future with 8 particles, shoot them towards the horizon, and I end up in the past with 10 particles. This is the same. This describes the same thing. Important thing is I have in the past less particles than in the future. Okay? But in that sense, we can get rid of something like this. And the new forbidden path is now the same. We measure positive energy into the past. I will visualize that as well in the future. But now we do an experiment which is time reversed, and therefore we need to impose the anti-Feynman prescription in that sense. And the Feynman prescription now is the right way to describe those processes, because then we get the convergence and we get the right path. Okay, good. Let's see how this looks like. Let's visualize that a bit. So we get, again, solutions to the Hamilton-Jacobi equation. We get some solution which is purely imaginary, and some solution which has 1 over CR, again with a pole. Okay, so that's a problem. But we can visualize it. So what have we done? So here we are in the future. This is past directed. We create particles, and we measure the positive energy particles in the past, and the negative energy particles tunnel through this horizon into the past. So this is good because here we have an anti-trapped region. The particle is then really trapped. So anti-trapped means past trapped. We go from R2 to R1, the same, negative energy. We get the pole, but now we have a different prescription, getting the same result. So what we see, okay, we get the same thing when we compare it to the Boltzmann factor. We get that we have an emission spectrum which corresponds to the Hawking spectrum, which we have seen, for example, in the black hole case. So this seems rather consistent or puzzling. I don't know. I cannot distinguish your faces, so it's half-half. And so I should say we have an emission spectrum into the past, and we found that this is an absorptive partner of the past inner trapping horizon. Why should I say that? I will show you later, but it's kind of important. So we see that quantum physics provides kind of a characterization of horizons into absorbing and emissive. And when we trace back this experiment, okay, we would see this would tunnel, this would go in the horizon, right? We would lose a particle. Okay, let's generalize it for the future inner trapping horizons. Then we're almost done. For example, a big crunch. Yeah, so the horizon is the future. It's an inner horizon because the normal region is interior, and the question is, can we go out of this region? And let's see, the forbidden path is the same. We have a negative energy particles tunnels outside, but backwards in time. We have the same problem. When we look at the crunch, all the stuff comes towards us, and when we then want to count particles and say, oh, what's the Hawking particles? This is kind of problematic because, yeah, it's not the same thing. It's not a clean experiment. How can we distinguish the particles? And we expect an absorption, but we'll do the same thing. So here we have the same thing. The observer sits here in the normal region. So the observer always sits in the normal region. We measure in the, so time goes up. This is the past here. So we say, in the future, we do the pair creation. The positive energy particles get measured in the past, and the negative tunnel through and is separated. And therefore, that's the idea, to separate those particles such that this can be measured and this is gone in that sense. So we go from the interior to the exterior, from R1 to R2. We have, again, an inner horizon. Inner horizon have negative kappa, negative surface gravity. I want to say here something. The surface gravity, from the interpretational point of view, is only for black holes really good understand, or at least I don't understand it, but maybe you understand it. So I would say this is the astronomical quantity which measures the acceleration rotationally and gravitationally at the specific surface. But for cosmological horizon, so I only found that this is something or some parameter connected to the temperature. In some sense, I would say, okay, I don't have a real interpretation for that, but if you have one interpretation, I would be very happy, actually. Okay, so this is for myself, or for also for the collaboration. Okay, so we get the temperature here, and we get an emission spectrum. This is all fine, and we have an absorptive partner of the future outer trapping horizon.
On this picture, you're envisioning a time-like horizon.
Yeah, this is okay. Yeah, this you should not take seriously. Yeah.
Just to even.
Okay, yeah, we can do it. We can do it. Yeah, we can do it.
Envisioning a time-like thing.
Okay.
And just to see, so in a big crunch, which is with a time-like horizon.
No, this doesn't work. Yeah, that's it. Well, wait. Let me think.
No, if you just take the matter-dominated or radiation-dominated universe and make it crunch in a space-like singularity, so it doesn't quite look like this. So you're thinking maybe an anti-de Sitter space or something where you can draw such a cartoon?
Yeah, this cartoon is not like a Penrose diagram. You're thinking in Penrose diagrams now, right?
Well, in any diagram, that's making
Okay.
the horizon space like a time diagram. That's it.
Okay. Okay, I answer. So this is not really referring to how the horizon is. Okay, I just said there is a horizon, and then we do that. But you're right, because here I draw the particles null, right? That's the point.
And your horizon has to intersect it, meaning you're only thinking of a time-like horizon for this cartoon to be to be interpretable even.
Yeah, that's true. Yeah, that's true. Yeah. So you say that the anti-de Sitter would have such a horizon.
I'm not an expert on that.
Is anyone? I don't know. So that I don't know. But of course we can also draw a space like, you mean like something like this.
The null line is tricky, but if you just take a normal big crunch universe,
Yeah.
then you've got a space like horizon.
That's true.
It's
Yeah.
hard to discuss anything crossing that. I mean, there is no other side, but your R2 becomes ill defined if you had a. There is no coordinate continuation for a space like singularity.
No, but this is not connected to the singularity
Or
now.
horizon, you forget about singularity.
Yeah.
The horizon is not.
Yeah, but the singularity is really like a hyperplane, right? So I cannot avoid the singularity. But the horizon does not need to be like a hyperplane. It is just like, it can be tilted like this, but it is not like that, right? So space-like does not mean it is one hyperplane. It's just like the angle is lower than 45 degrees.
Yeah.
Yeah. And therefore, I don't see why I cannot cross this horizon.
No, this one you can cross, but if I.
Oh, wait. When I have a.
Where would you define R2 to be?
When I have a space like horizon, like this, so this is null. Why can I cross that?
So which way is?
That doesn't matter. So, okay, let's think. Okay, yeah, let's think.
Horizons are defined as null surfaces usually. Like the horizon definition is.
No.
spaces that-
Not in the dynamic case. No, in the dynamic case, not. The static horizon is a null surface. A dynamical horizon can be space-like or time-like. And here we have, it is almost null. That I said, I don't know whether you were here in the beginning, because we have dynamic horizons where we have an equilibrated horizon. We can draw a picture. We can draw a Penrose diagram. And let's say we look at some collapse. So here, this is the usual picture. Here we have the event horizon, right? So now when we want to have a dynamical horizon, this will form in a different way. So it can be like this, and then it equilibrates to the event horizon, but only in the infinite future. So it will, at square plus, will reach the event horizon and will be indistinguishable. Here, it is still something. So here it can be space-like, it can be time-like, but it doesn't mean that it's.
I mean, basically what you have, you've got a dRdu and dRdv both being negative for this to be a trapped surface. But if you think of just a because in normal cosmology we think of either let's take a radiation-dominated universe. Well, its Penn diagram is a square, so where there is no there is no place where you have a region where theta plus and theta minus have the same sign. I mean, in the normal. That I'm aware of.
I'm not sure whether this is right. So you can. Well, why can't you have something like this?
I'm just saying what you need is a dr. If I foliate my space with no lines in and out using these.
Yes.
And what you need is that along both lines, my r is decreasing with the u and v, right? Just in spherical symmetry.
In the trapped region, yeah.
Yeah, the trapped region. So if you h is envisioning that there is a trapped region. That's what you mean by. I think that's what you mean by RH. Is that there is a region which is trapped.
Yeah, beyond RH, there's a trapped region. Yeah.
Think of an example.
Yeah. That's the problem. That's what I'm saying. Those horizons can occur, but it's hard to think about in a real. Do you want to say something?
I think the horizon he's defining is actually slightly different from what you are talking about.
Think like this.
No. I just follow him. This saying what he wants is he wants the area of the surface.
Yes.
And you can define the area surface that you go on ingoing and outgoing null ways.
Look.
And he wants both of those to have the same sign, that you go in or out,
No.
they both get larger. Both
Yeah, but in this region, let's see. Here we have a Penrose diagram, and I can draw a region which is trapped here. So here.
I agree that in principle you can, but I'm just trying to think of, can you give me an constructive example where there is a horizon in a cosmological context that looks like a crunch? Can you name something for which this, is there a known metric for which there is such a surface?
Yeah, for this Badin metric, you can construct that.
For Badin metric, what kind of universe is that?
Let me think. Is it the equation of state parameter 1 universe? I think. Equation of state W equals 1.
1.
I think it is some. I will look that up. I'm looking. Yeah, no. I'm looking that up. No, I know there is something like that, but I will look it up. You just have to tell me what your name is, and then I will come to you and explain.
My name is Penn.
Oh, okay. Oh, you're the director. I'm sorry. I'm screwing everything up here. Okay. Oh, this is recorded. Okay. So let's check whether this is consistent. Okay, let's go into the discussion, check whether this is consistent. Okay, I should have switched the microphone off. Okay, let's ask the question, what if we use the Feynman prescription instead, right? We want to make real experiments, and real experiments we do not do in the past. So that's kind of, yeah. Okay, so to mean using the Feynman prescription means perform the experiment in the future. That's what I say. That's same. So here we see the thing. We have a particle equation, and we want to send the positive energy particle in the trapped region and the negative energy particle into the normal region where it is measured. So now we need either to have a device for negative energy particles measuring, or we need to come up with different experiments. So in that sense, we have an emission of negative energy particles, and this means the observer counts more particles in the past than in the future. So I can start with 10 particles in the future, and then I look and I see, oh, there comes the negative energy particles. It's kind of, annihilating my positive energy particle. And in the end, I have, after some measurement, I have only 8 left. So that's kind of consistent. This seems consistent, but let's see. Now we get a negative imaginary part, which seems now a bit weird. And, but we should think about that we have an emission of negative energy particles here. That means we have the following tunneling rate. But now we have a positive sign. So it seems not to be exponentially suppressed. But what do we have to compare? We have to compare that rate with the thing we measure. So that means the negative energy particles. And we should compare them. Now the emission over absorption is minus, and then we get another minus from the energy. So this would be just intuitively fixing a negative energy and then comparing the same. This is, of course, not so physically, making negative energy, but I just want to say here, the emission of negative energy particles would then have the same sign as this, so it is kind of comparable. But the easier thing is to say, okay, the absorption is now exponentially suppressed, so therefore it is intuitive that we get an absorption in these horizon types. But the problem is now we send a particle in the trapped region, for example, in a crunch, and the geometry would force the particle to go out again. So this seems like this is a temporally limited effect, that the particle can stay in the trapped region. And the probability that the particle gets forever there is approaching 0. And this would, for example, slowing down the process when we think about the white hole, which spills out stuff. This would enhance the white hole lifetime because some particles go in from the Hawking effect and then get spilled out. So it probably it's not a big effect, but it can enhance the white hole lifetime. This is just our proposal, but that's the first order process. We don't know. There's no back reaction and other things. So in that sense, I just want to say that. So, and let's wrap that up. Okay, we saw that all horizons are subjected to an Hawking effect with the temperature. In that sense, when we kind of do experiments such that we get an emission, then we found that we have a characterization in emissive and absorptive horizons due to the quantum effect. And we saw that the tunneling was very useful for that because it was straightforwardly generalizing. And now we should talk about systems with more than one horizon, because then it becomes clear why the absorption and the emission is actually very intuitive when we have cascading horizons. So let's go into Reisner-Nordström black hole. Reisner-Nordström black hole has a space-like singularity. And yeah, let's say this table is the trapped region. Here's the exterior. Here's the interior. Interior is a normal region, so we have an observer here. And we have an observer here. So the observer here, when we think about, OK, this black hole, let's assume this black hole evaporates. Let's just assume that for a moment. Then what does it mean? I sit here as an outside observer. I count the particle coming out. I would say, OK, now, with the picture we used, we have the split. The negative energy particle tunnels inside, and the positive energy particles is measured by me. So I would say, OK, the black hole should have lost energy. So let's see. The interior, how would he describe the black hole evaporation? He would say, OK, he would measure the emission of a negative energy particle, and the positive energy particle heads tunnels out. So he would say, OK, oh, I lost energy in my interior. So now in the trapped region, what do we have left? We have from the interior, a positive energy particles has tunneled in the trapped region, and we have from the outside, negative energy particles trapped here. So they would recombine, and everything is fine. So this is the same as taking the energy from this observer, sending it through the trapped region outside, and is measured by the outside observer. So in that sense, to have absorptive and emissive horizons, and that those are the partners, those are the partners, is kind of intuitive from this cascading. Yeah, and the last thing is, yeah?
If you want to make this as a Hawking effect, you've got to argue that the person on the inside horizon is shining the right vacuum at his horizon, otherwise you see the wrong number of particles coming out.
Yeah, the number of particles, that's true. The number of particles has to be fixed and adjusted because we also have to describe the traveling through the trapped region, which is also non-trivial. That I agree. So I would not say that we are now at the point we can say this is fully understood, but from the intuition, it should be like that, right? So when we really assume this black hole evaporates, then we need to have one absorptive and one emissive part. That's just what I say. I don't say the particle number are identical. Agree. This is not what I'm saying. I totally agree. So the Hawking effect here is connected to semi-permeable horizons. What does it mean? That means horizons which induce a pole, and when we have such a pole, we get a non-zero Hawking effect. But what has been done by Vanzo Zerbini and collaborators, that when we look at static traversable wormholes, those horizons have they have a pole, but this pole is not a harmful pole, and this pole is essentially, we can think about it has no pole because it's traversable, right? It's not semi-permeable, and therefore they found that there is no Hawking effect for such geometries. Yeah, that's what I wanted to say. Thanks a lot.
So we already had quite a lot of discussion during the talk, but does somebody have more questions, comments?
Yeah, please. Yeah, you can have as many as you want.
So obviously this is a nice way of describing a horizon locally, which normally is difficult to do. Now there are these experiments, tabletop experiments people do with water tanks. So you have a supersonic, supersonic to the surface waves, and you send waves in, and there's a white hole set up, and then you look at how these waves absorb, and then the claim is that this may or may not map onto a Hawking process.
Yeah.
Does your thing work on it? Does your calculation work on surface waves on water?
I haven't checked that. I don't know, but it would be very interesting to do that. Actually, you mean like the analog, it's like analog gravity experiments, and to compare this, we haven't checked that actually, but it would be very nice to do that.
Exactly.
It's a very good idea.
Description of it, whereas normally
And we have a tabletop. We can really prove.
you can compare with experiments.
This is a very nice idea. Yeah, but okay, I will ask you later. I will. Yeah, this is very interesting.
More questions? Okay, if not, let's thank Marc again.
Thank you.